Assalamualaikum warahmatullahi wabarakatuh. I'm from group 28. Will present the project we have done. My name is Nur Wahid bin Samsudin, number metric DAE21203. Our group consists of 4 members, including Russell, Shahadi, and Ding Hui. First, I will explain the introduction to this project. Digital electronics cover a broad range of electrical engineering topics focused around the design and operation of digital systems using logic circuit and flip-flops. Oftentimes, digital applications require counter finite state machine and register in order to control, store, and process digital information. Counter a sequential logic circuit which count the number of clock pulse input and provide a specific binary output sequence. Counter can be found within digital clocks, timer, frequency divider, even counting system, and station. Because counter can be designed to count in any specific sequence, they are extremely useful for control and timing applications. Finite state machine, or FSM, are digital models that are comprised of a finite number of states. Transition between these states occur when input signal and clock pulse are applied. FSM can be used to control how a digital system will behave, specifically when operation need to be performed in a certain order. For this project, a more machine FSM was implemented with checker flip-flops to produce a unique count sequence. Register a group of flip-flops that are used to store bits of binary data for a short amount of time. Register are used often in digital system to store, transfer, and process data. Shift register allow data to be shifted or moved from one place to another. These types of register are usually used in communication. Next, I would like to explain the objective of our project. This project was carried out with several objectives that help us gain a deeper understanding of digital electronics and its practical applications. The first objective was to understand the operation of finite state machine, or FSM, counter, and register. These are important components in digital system because they are used to control operations, consequence, and store data. To achieve this, our second objective was to develop the state diagram, state table, and excitation table for the FSM design. The state diagram shows how the system moves from one state to another, while the state table and excitation table help determine the inputs required for those state transitions. The third objective was to simplify logic function using Carnot maps or K-maps. This method helps reduce the complexity of Boolean expression, making the circuit design simple, more efficient, and easier to implement. After simplifying the logic function, our next objective was to implement the FSM using JK flip-flops and logic gates. This component we use to create the design state transition and outputs required by the system. In addition, we aim to construct a 4-bit parallel in loop recalculating shift register. This This register allow data to be loaded simultaneously and then shifted through the system according to clock pulses, which is an important concept in digital data processing. Finally, the last objective was to verify the designed circuit using Tinkercad and Logisim simulations. The simulation tools allow us to test the circuits, identify any error, and ensure that the outputs match the expected design before implementation.
Alright, so now I will to present about task A. So we design a custom sequence of finite state machine as showing in our state diagram and also the state table. So the circuit cycles through an 8-state closed loop and beginning from state 110 and moving to 010 and then stepping through 001, 100, 101, 011, 111, 000, and transitioning back to 100. So to implement this sequence, we using standard JK execution table as our reference guide to determine the required inputs for our 3 flip-flops and mapping out the complete FSM agitation table shown in the slide. So by plopping the value into the K-maps for each input, we derive the simplified Boolean equation for our 3 JK flip-flops. So for the first flip-flop 2, which is Q2, for the first input, JK2 is equals to Q2 or bar Q1 or Q0. And for the second is KQ2 is equals to Q1 or Q0. So for the second flip-flop, flip-flop 1, and inside the first input, JQ1 is equal to bar Q2 and bar Q0 or Q2 and Q0. Actually is same with same concept with X NOR, and for the input KQ1 is same with the JQ1 X NOR, Q2 and Q0. So for the third flip-flop 0, inside the J input inside the flip-flop 0 is equals to bar Q2 and Q1 or Q2 and bar Q1. So actually same concept with XOR gate. And for the second input, K input inside the flip-flop 0 is Q2, bar Q2 and bar Q1 or Q2 and Q1. So actually it's also same concept with XNOR. So after that, to using those exact Boolean extraction, we first construct the schematic diagram inside in Logisim and wiring up the logic gates to the J and K inputs for the 3 flip-flops Q2, Q1 and Q0. So inside the Logisim, we using 2 OR gate, 1 XOR gate and also 2 XNOR gate. To when we build the simulated physical equivalent circuit in the Tinkercad, we using 274HC73 dual JK flip-flops IC, and alongside 7HC32 OR gates, 7HC X6 XOR gate, and also 74HC04 gate NOT gate, and we using the power by 1 hertz of the clock source. So the simulation was successful, and may looking at our table result, you can see that at clock pulse 0, the output start at 110, and the shift exactly along our target sequence 010, 001, 100, 101, 011, 111, and after that returns perfectly to 000 at the clock step 7. So that's all for task A.
My part is about the shift register. What is a shift register? A shift register is a sequential logic circuit used to store and transfer binary data using flip-flop. In this project, we designed a 4-bit parallel inline recirculating shift register using 7476 JK flip-flop to demonstrate how digital data can be stored and shifted within a circuit. The main concept of a shift register is to store data and move it from one flip-flop to another based on clock pulse. In our design, data is loaded simultaneously through input A, B, C, and D using the parallel load method. After loading, the data is shifted to the register with each clock pulse. The recalculating feature allows the output data to be feedback into the register, enabling continuous calculation of the data pattern. This figure shows the 4-bit parallel inline recalculating shift register built using 7476 JK flip-flop. Each flip-flop stores 1 bit of data, allowing the circuit to store a total of 4 bits. Input A, B, C, and D are used to load data in parallel, while the clock signal controls the movement of data through bit register. With every clock pulse, the data shifts to the right. The circuit also uses a recalculating connection, where the output is feedback into the input, allowing the data pattern to calculate continuously. This demonstrates the basic operation of a shift register in storing and transferring digital information. So, the result we can get is the circuit operates as expected. The clear function successfully reset all output to 0, while the parallel load function correctly loaded the input data into the register. During the shift right operation, the data moved to the register according to each clock pulse. Therefore, the result confirmed that the parallel inline recalculating shift register was successfully designed and functioned correctly according to the project objective.
In conclusion, this project was successfully completed and all objectives were achieved. The finite state machine circuit was able to generate the required counting sequence correctly, while the 4 bits parallel inline recirculating shift register operated as expected during loading and shifting processes. The simulation result matched the theoretical design, proving that both circuits function correctly. Through this project, we gain a better understanding of FSM, JK flip-flops, counter, and shift register, while also improving our digital circuit design and simulation skill. Thank you!